Good morning, everyone. Welcome to the AP Physics 1 and 2 open house. If you have any questions, you can stop and ask me. You can put your questions in the chat box too. Okay, and if there's any problem with sound or video, just warn me. Okay, we can fix it. All right, so again, welcome to open house AP Physics 1 and 2. My name is Ibrahim Albayrak. I have a PhD in experimental nuclear physics, so I'm an experimental nuclear physicist for a little while. But in addition to that, so I have done most of my experimental nuclear physics research at Jefferson Lab in Virginia. It's a national nuclear research facility here. So I have done my majority of my research here. I have done some research at Fermilab and in other national labs throughout the United States and some other labs in other places in the world. In addition to my research, I still continue my research there. So my nuclear research, nuclear physics research. In addition to that, I'm teaching modern physics classes, quantum physics, nuclear physics, Einstein's relativity theory, special relativity, and general relativity. Those stuff, Governor School for Science and Technology. In addition to physics, modern physics, I also teach C++ programming, computer programming classes, and some engineering, design, and construction classes. That's who I am. You can call me Dr. A. That's how my students most of the time call me. And again, if you have any questions throughout the open house, just stop and ask. That's okay. We can make this an interactive thing. I'm okay with it. Today, this is what I'm going to do. Today, I'm going to introduce, of course, the courses where I'm going to be teaching this summer, Physics 1 and Physics 2, AP Physics 1 and AP Physics 2. So before I just describe the contents of Physics 1 and Physics 2, I want to talk a little bit more about what is physics, meaning of physics in general, the science of physics, because probably some of you guys have little information about the content of physical sciences. So I'm going to start from there quickly and then describe what physics is, and then I'm going to go ahead and start describing the physics, part of physics we're going to be learning this summer. So physics is all about, probably you already know, understanding the nature, understanding universe, the study of structure and machinery of the universe, right? So part of this, like understanding essential building blocks of the universe, matter, light, atoms, molecules, etc. Essential building blocks. What is matter composed of? And then another part of physics is the interactions between these building blocks. Right? How do they interact with each other? Or how many types of interactions we have, right? Electric interaction, mechanical, I don't know, nuclear interactions, etc. Right? And then one other side of physical sciences is structure of space and time. So everything happens in space and time. So are these things just a uniform, flat background for physical events, or do they also contribute to the physics? Space and time itself, do they contribute to physics? So this is also a topic in physics, especially in terms of Einstein's relativity theories. So those are just theories that incorporate space and time and structure of space-time into physical sciences. And then in general, physics also discusses evolution of the universe. So using physics, we try to understand the universe. All right. So next thing I'm going to discuss is how much do we understand the universe? So is physics, I mean, at its highest level right now, right? So the question is, there's the universe there, and then how much do we understand the universe in terms of physical sciences, right? Or where are we at in understanding the universe? So first, we need to define universe. What is universe? So we can only talk about universe that we can see. That's what we call observable universe, right? So that means there is a part of the universe, maybe the biggest part of the universe that we cannot see. We are not allowed to see beyond our horizon, right? So there's the part of the universe that is beyond our horizon. We can't see it. So we cannot know what it looks like and what are the interactions, what is the physics there. There's no way for us to know. So the only physics that we developed so far as humanity, that applies to the observable universe, which is probably a very small portion of the whole universe or the whole existence, let's put it that way. A very small portion of it. And the size of the observable universe as we know it today, as far as we can see, it's 93 billion light years. A light year is a distance a light ray travels in a year. So it's a very long distance, and the observable size of the universe is approximately 93. It's, you can say, 100 billion light years. And then there's the universe beyond that that we can never reach and see and conceptualize. So when I say universe, when we say universe, we're always talking about this observable part of the universe, not the whole universe or not the whole existence, right? Let's talk about this universe then, right? How much of it do we understand? How much of it can be explained through our physical sciences, right? So at the beginning, I want to say this. So even the observable universe, we only understand only 5% of the observable universe. So the rest of the 95% of the universe is still unknown. I mean, the physics of it is still unknown. We don't understand the rest of 95% of the universe. So today, whatever the physics, I'm going to have it in these slides, right? Quantum physics, nuclear physics, quantum electrodynamics, chromodynamics, classical physics, Einstein's relativity theories, all of these theories explain only this 5% of the universe. So what is the other 95% of the universe? Or how do we know there is the 95% of this observable universe? So there are these. So this 5% of the universe we're talking about is called as ordinary matter. So it's just atoms, molecules, and stuff that we are familiar with, right? The planets, stars, galaxies, all of these makes up only 5% of the universe. And that's the physics we are doing. We're trying to understand this ordinary matter, right? So how do we know there is other things that makes up 95% of the universe? So the other almost 30% of the universe, we call it dark matter. What is dark matter? Well, if we knew it, we wouldn't call it dark matter. So we don't know what that is, right? That's why we call it dark matter. Then how do we know there is dark matter, right? There is such thing as dark matter out there in the universe, in the observable universe. Well, so maybe there's no dark matter. So that's a funny question. But when you observe, for example, your galaxies, I mean, I'm going to give you a simple description of it. When you, for example, look at galaxies, I'm going to draw a galaxy here, right? The motions of galaxies in space. Use your telescope, watch the motion of galaxies. So you're going to see some weird motions in space. So galaxy, for example, this galaxy, for no reason, you're going to see that it turns its directional motion. But there is no obvious reason for this motion. I mean, it should normally go straight, right? But it doesn't do that. And then it just changes its course. So obviously there's a force, right, acting on this galaxy in this direction. But the weird thing is there is nothing here that we can assign this force, right? So we call something that is called dark matter here. So we don't know what that is. Is it an ordinary? I mean, what type? It's not obviously an ordinary type of matter. So it cannot be composed of atoms and molecules and stuff. It's not stardust. All right, it's something else. The only thing we can attribute to it is it has gravity. So that's why we call it dark matter. So the only thing that it can have gravity. Other than that, it cannot be composed of atoms and molecules. So, or protons and neutrons, anything that we know of. So this is what dark matter is, right? So we observe the motions of galaxies and stellar stuff, and then we deduce that there must be other stuff, and the amount of this stuff is way more than the regular matter. So the amount of the dark matter is 30% of the universe almost. It's more than 5 times the ordinary matter that exists. I mean, planets, stars, galaxies, etc. Right? So this is our current understanding of the universe, right? Maybe there is no dark matter. Maybe our theories are wrong, right? So that's also possible. But for the moment, this is how we explain the motion of galaxies. There must be something that is called dark matter. And still, this is an active research, so people are looking for dark matter. And then the other thing, so still we are at 30% of the universe, 30, 35, right? So what is the rest of the universe then? The almost 70% of the universe is called dark energy. Again, if we knew what that is, we wouldn't call it dark energy. So that's also something that we don't know, that we cannot explain using our theories, right? So what, and then how do we know there is such thing as called dark energy? Well, it's about the expansion rate of the universe. So one thing we know about the universe, it's expanding. Because if you look at the galaxies and stars, everything is going away from each other. So that means our universe is expanding, and the expansion rate of the universe doesn't also make sense. Because as you know, I mean, people who knows gravity a little bit, gravitational forces are attractive forces. Normally, gravity between Earth and Sun, it's an attractive force. That's how we have our solar system, for example, right? So, and everything in the universe that we observe, galaxies, stars, planets, everything, they have gravity, and everything actually pulls everything, right? So normally universe, I mean, in a naive way, shouldn't be expanding. It should be collapsing, right? Universe should be collapsing because everything is attracting everything else, right? But universe is expanding, and this expansion rate also doesn't make sense because it's expanding in an accelerated way. So we then reason and say that there must be another type of force, another type of energy that we cannot explain using today's theories that cause this huge expansion of the universe, that drives this expansion of the universe. And that energy, we call it dark energy because we don't know what that is yet, okay? And again, so maybe there is no dark energy. Maybe our theories are not totally correct, but that's our current picture of physics. So we are dealing with only observable universe. Let's go back one step. And then in the observable universe, we only understand, I mean, our physical theories apply to only 5% of it. The rest of the stuff, we're still trying to understand, okay? So this is the humble picture of our understanding of universe. So let's go to the theories of the physics, and then specifically the physics, part of physics we're gonna be learning in this course. So I already talked about universe. So when I say universe, I'm only referring to the visible universe, observable universe. And then in the observable universe, I'm only referring to the 5% known matter and interactions of known matter. So that's almost the size of the universe is almost 100 billion light years, right? So, and then in smaller scales. So physics is all about, right, universe from largest scales to the smallest scales we can reach. So in the largest scale, we have the universe. In smaller scales, we have galaxies. I mean, there are structures between them, like clusters of galaxies. I'm not going to spend too much time on these things, right? And then, like, average size of a galaxy is 30,000 light years. So it's pretty small compared to the size of the observable universe. And then in even smaller systems, smaller structures, we have systems like solar system, like planet systems, etc., and stars. And then our planet system, the size of it is almost 9 light hours. So we're not talking about light years anymore because it's way smaller compared to the size of a galaxy. So light years as a distance measurement becomes irrelevant here. So we start referring to distances in kilometers and more familiar units. So the size of our solar system is about 9 billion kilometers now. And then even in smaller scales, I'm going to call it human scale, so meters, right? So this is where classical physics enters. So the physics we are going to be discussing is the physics that applies in this scale, right? Even in smaller scales, we have molecules, large molecules, small molecules, and then atoms, even smaller scales. So molecules have 10 to negative 8 meters sizes, average size. Atoms have sizes 10 to negative 10 meters. We call it 1 angstrom, another distance unit. And then even in smaller scales, we have subatomic particles, electrons, protons, neutrons, that make up all the matter we know of, the ordinary matter. So these guys, these three guys, are the only things that make up the ordinary matter. Okay, in ordinary matter, we don't have anything else: electrons, protons, and neutrons. That's what we refer to as ordinary matter in the universe. That's everything that these three guys makes up everything in the universe we can observe. And then even in smaller scales, in proton and neutrons, we have quarks and gluons. So that's the smallest limit we know of. So quarks and gluons, we don't know anything smaller than that. And we don't know their sizes. We don't know electron size too. So we're just saying 0 meters, and then quarks and gluons same. So we cannot measure their sizes. But protons and neutrons, they are about 10 to negative 15 meters, their sizes. That's what we call 1 Fermi. All right, so as I said, so the physics we're going to be learning this summer, Physics 1, AP Physics 1, AP Physics 2, is related to human scale physics, applies only human scales. So what about the other physics that applies in larger scales, like the universe as a whole, or galaxies, planet systems? It's most of the time general relativity explains those, the evolution of the universe, Einstein's theory of general relativity. And then in smaller scales, molecules and atoms, quantum physics works there. And then even in small scales, quantum physics doesn't work there. So we invented new physics. Quantum electrodynamics and quantum chromodynamics are the physical theories that explain in subatomic level, in nuclear level. And let me put it this way. So in nuclear level, we're still developing these theories. QED is pretty much developed theory, but QCD, quantum chromodynamics, that is the physics of quarks and gluons. We're still developing it. It's not complete yet. And that's my area of expertise, so nuclear physics in terms of quarks and gluons, quantum chromodynamics. That's an active research area today. All right, so this is the physics in general that explains the observable universe, and then the physics we're going to be discussing this summer is just classical physics, Newtonian physics, sometimes called Newtonian physics, and electromagnetism. That's what we're going to be doing this summer. All right, and all of these theories, let me go back one step. All of these theories explain only 5% of the observable universe. So if you ask a question, I mean, how much do we understand, right? That was the first question I asked. How much do we understand the universe? Well, we understand the universe this much, right? It's not much. All right. So we're going to have 2 courses this summer, AP Physics 1 and then AP Physics 2. AP Physics 1 starts on June 28 and August 19. Total 48 hours. This is going to be 8 weeks course. It's going to be like a little compressed. AP Physics 1. AP Physics 2, it starts July 9 and until October 29. So unlike AP Physics 1, this is 16 weeks. So same amount of time, still 48 hours, but this is going to be 16 weeks. AP Physics 1 is going to be 8 weeks. Okay, a little more compressed. And then prerequisite for Physics 2 is AP Physics 1, and you're going to get 5% discount if you register and pay by April 30. That's what they say. All right. And again, stop me if you have any questions. Okay. All right. So AP Physics 1, that's the introduction to physics. That's the first step into the physics, right? Everybody takes this as the first course in physics before taking everything else, right? So our focus is going to be mechanics, similar to what is covered in AP Physics 1. And I'm going to be focusing more on concepts, and pace will be slower. But as I said, so this summer, it's going to be a little compressed compared to the Physics 2 course. There's going to be weekly homeworks. So this is what we're going to be doing this summer. We're going to be meeting every Wednesday and Saturday for 3-hour sessions. So between 5 p.m. and 8 p.m., 3 hours. 2 hours of this is going to be lecture, and then 1 hour is going to be homework solution. So we're going to be solving the problems of the previous week, right? So that means every week we're going to be spending 6 hours together on Wednesdays and Saturdays. And then those who prefer, they can take the next class, F equals MA preparation class. This is a competition. So that would be the next level for you guys. So these are the topics. So this is divided into 16 weeks, but remember, so we're going to be doing this in 8 weeks. So for example, here week 1 and week 2 is going to cover these. I mean, week 1 is going to cover, for example, week 2 stuff too, right? So we're going to be doing all these in 8 weeks in the summer. Next semester, I mean, fall semester or spring, it's going to be 16 weeks again. We're going to have a midterm and a final exam. And then again, every week there's going to be homeworks. So that's how we do. So I'm just going to quickly talk about the stuff we're going to be learning in AP Physics 1, right? Vectors, laws of motion, energy, momentum, rotational motion, etc. So we're going to start learning some concepts in physics first, right? Some concept that is helpful for our understanding of physics, and we also learn about we define some concepts like position, coordinate systems, measurements, numbers, significant figures, etc. Right? So we're basically developing the background for learning physics here. That's the first thing we're going to be doing, and then we're going to start learning motion in 1 dimension. So this is just purely motion in 1 dimension. So what the relationship between position, and we're going to define speed, like concepts like such as speed, velocity, acceleration. And then we're going to discuss the relationship between position of one object and its speed and its acceleration and its velocity only in 1 dimension. So only in 1 dimension, the motion or kinematics in 1 dimension, right? So we're going to develop these concepts here: position, velocity, momentum, not momentum, sorry, acceleration, and the relationship between them. And then we're going to start discussing vectors, some other important concepts in physics, because in physics, many concepts are described in terms of vectors. So we're going to discuss vectors, learn vectors, and then discuss motion, kinematics in 2 dimensions. In the previous case, we start discussing motion in 1 dimension. So in here, we are going to be dealing with objects moving only in 1 direction. And then we're going to generalize this here and then start discussing motion in 2 dimensions as given in this example. So vectors are going to be important in understanding of these concepts. Next, so far we have learned motion in 1 and 2 dimensions. So position, velocity, speed, acceleration, but we haven't discussed anything related to the cause of the motion. So what makes objects move, right? What's the cause of the motion? So next, that's what we're going to be dealing with. So forces, right? Forces are the stuff that that makes objects move. So we're going to discuss here Newton's laws, and then the relationship between forces and motion. Not only forces and motion, we're going to be also discussing static systems, right? So especially these are important, especially for example, civil engineering, right? So when you're designing buildings or bridges, right, they are static objects. They are not moving, but there are still forces involved there. So understanding the forces in static equilibrium, that is important too. So in addition to motion with forces, we are going to be discussing also static equilibrium systems. Here, we're going to be also discussing gravitational forces, every type of forces we're going to introduce. Next, we're going to discuss work and energy, very important concepts in physics, work and energy theorems. And also, we're going to define them or define work in physics. The definition of work in physics is different than the definition of it in daily life. So we're going to define work, and then we're going to define kinetic energy. Then we're going to define work energy theorem, the relationship between work and the kinetic energy. And then finally, we define potential energy, another type of energy. We're going to also discuss power, right? The concept of power. So that's what this chapter's topics. And then next, we're going to discuss momentum, impulse, and collision. So far, we have been discussing, objects moving in one or two dimensions, and then motion is caused by forces. But there are other things in physics, right? Not only just motion or displacement in space by a force. Sometimes there are explosions, right? Or collisions, etc. This kind of stuff. So you cannot describe explosions, collisions with the stuff we have learned so far. So here we learn momentum and impulse, concepts of momentum and impulse, which helps us understand collisions, explosions, these kind of phenomena in physics. And later, so almost everything in the universe, from smaller scales, as today everyone knows it, right? From larger scales, from galaxies to the smaller scales, to the atoms, everything actually rotates in the universe. So rotation or angular motion is very important in physics. So we're going to start learning or developing concepts of angular motion, right? So, and then we're going to develop equations for angular motion. And then just like we did for linear motion, right? So remember, we learned first motion in one dimension, positions, velocity, acceleration, and relationships between them. And then we introduced the cause of the motion, which is a force. So we do the same thing here. First, we develop concepts in angular motion. So in analogy with linear motion, we're going to be defining angular position corresponding to position of an object. And then we're going to define angular speed, angular velocity, and angular acceleration, just like we define position, velocity, speed, acceleration in linear motion. So we're going to be defining these, right? Angular position, angular speed, angular acceleration. And then we are going to go ahead and then introduce the cause of angular motion. So why objects rotate? Basically the force, right? We're going to introduce force or rotational dynamics. Right, so we're going to involve forces and then their effects in rotational motion in this part. That's going to be the last part of our AP Physics 1. So this is what AP Physics 1 looks like. And then AP Physics 2. So I already told the dates: July 9, October 29. And then since this is 16 weeks, we are going to be meeting only one day on Sundays between 5 and 8 p.m. So we're going to be meeting only 3 hours per week. 2 hours is going to be lecture again, and 1 hour is going to be problem solving of the homework questions the students have in the previous week. All right, and then so here our topics are fluids, thermodynamics, electric force field, potential electric circuits, magnetism, electromagnetic induction, geometrical and physical optics, and then some modern physics concepts like quantum physics, atomic. Of course, we're not going to be learning these in detail, just quickly overview of these concepts. All right, so fluids are here. We're going to be learning like concepts like buoyancy, pressure, relationship between pressure and volume, those kind of stuff. And thermodynamics is mainly related to heat and energy stuff. So we're going to be learning the definition. We're going to define heat and then change in the internal energy when you add some heat and the work. So relationship between heat, work, and energy. Again, the concepts of pressure, volume, and temperature is crucial concepts in this chapter. So we're going to be learning basically those. And then electrostatics next. In electrostatics, we're going to be learning interactions of electrically charged objects, right? So like charges repel each other, unlike charges attract each other. And then we're going to learn force fields or electric fields that explains these interactions in terms of fields. And then we're going to learn Coulomb's law that gives us functional form of these interactions, electrically charged objects. And then we are going to discuss electric circuits. We define different electrical components like wires, resistors, batteries, switches, etc. So the components that is used commonly in electrical circuits. And then we are going to be discussing how these are combined to make a circuit, and then features of these circuits. All right. Then we're going to discuss magnetism. So objects can have electric charges, but they can also have magnetic properties. So this is a different concept than electricity. So we're going to be discussing this magnetism and then magnetic field concept. And also we're going to be discussing electromagnetic induction, or magnetic induction in short. Basically, generation, I mean, how do we generate power from power plants, for example? That's basically magnetic induction. Or how do we run electric motors, or how electric generators generate electricity, etc. These kind of concepts, how motion of magnetic objects create electric currents. That's basically what it is. And then after that, we are going to start discussing optics. Mainly it's going to be ray optics, geometric optics, in other words. So in this discussion, we are going to learn how to use lenses and mirrors, different types of mirrors, concave and convex mirrors, concave or convex lenses, and how to construct images, etc. So we're going to be learning these here. And then finally, we're going to learn some concepts in modern physics. So we're going to be learning what quantum theory does and what is it all about. Of course, not in the details. So quantum theory, as I said at the beginning, it's all about atomic level phenomena, atoms. It explains basically atoms. And then nuclear physics. Nuclear physics is all about the nucleus of atoms, because quantum theory doesn't work there. So the physics theories, as I mentioned in the beginning slides, they have their own application, domain of application. You cannot apply quantum physics to large scale universe. For example, quantum physics does not explain large scale physics like galaxies, planets. So, and then there you had Einstein's general theory of relativity. You cannot apply it to atoms. It doesn't explain atoms. So every physical theory has their own domain of application. So quantum theory similarly doesn't work for nucleus. So we need to invent a new type of physics. But unfortunately, nucleus, we still don't have a consistent theory of physics. So that's still a mystery there. So we're still struggling to understand nuclear physics or nucleus in terms of nuclear physics. And then in even smaller scales, we have protons and neutrons, quarks and gluons. That's quantum chromodynamics. And then, as I said, so we're still developing those theories. So here in short, in the final part of this course, I'm going to be discussing superficially the modern physics concepts. Right, the relationship between the energy and mass. You see here E equals mc squared. That's famous, maybe the most famous equation in physics. So the meaning of it, etc. All right, so that's that. So here I think this is the end of my slides, my introduction, or my open house. So you guys can go ahead and ask if you have any questions to me as an instructor, or if you have any other questions that I cannot answer, I can take them and then relay them to the administrators, etc. Or you can send them emails or messages, call them. So let me know if you have any questions so far. These are the office hours of the momentum learning administration, I guess, so you can reach them. So thank you very much, everyone.